Our next speaker here is Chris Gottwald, and he is now the Chief Data Scientist at JUMP. And he's also been kind enough to come to at least 2 or 3 DataWorks before, and even he did one Army conference on applied statistics before this. And he's going to be talking about a relatively new method, which I think is pretty exciting because it's the small data problem. And we're actually hearing about that, I think, at this conference. And I'm just going to let him, you can read the title here. I'll just let him talk about this.
I can knock into this one. Well, thank you, Tom. Thank you for having me back here. So I'm going to be talking about software and validation, but in a totally different context. So of course, I work for JUMP, and I'm going to be talking about validation, but this is in the terms of kind of machine learning model selection validation. And we're seeking ways of doing that kind of thing with the very small data sets that are typical in DOEs. And also, I know that here in the DoD, it's very, very common to have very small end problems. So we're trying to bring machine learning type techniques into these small sample sizes. So this is work that I did in collaboration with Phil Ramsey, a professor at the University of New Hampshire, and Trent Lemkes was our PhD student who really did all of the work here. He really deserves to be the lead author on this because this is all his effort. And I'll go ahead and get started. Okay, so DOE analysis, as I've seen it be practiced in industry for the most part, is really pretty much still based on slight variations of least squares, linear least squares analysis, and ANOVA type techniques. And this has been the case since at least the 1970s. Now, we hear in the news every day about remarkable new things that machine learning is capable of doing, but this hasn't really had a whole lot of impact yet on the analysis of designed experiments. Now, however, the improvements that we're seeing in machine learning in the big data area, we're often hearing about greater accuracy of these techniques. And if we're able to bring them into a design of experiments context with small n's, it has the promise of allowing us to innovate faster and with lower cost. So there's a definite value in trying to achieve higher accuracy with these small data sets. So the technique we're talking about here, SVEM, is what we call it, Self-Validating Ensemble Models. This was our what emerged as the best technique that we were able to come up with in this context. And if you're familiar with the technique of bagging or of random forests, it has a very similar, it's very similar in spirit, except that instead of using the resampling-based bootstrap, we use a kind of a carefully retooled version of what's called the fractionally weighted bootstrap, and I'll be explaining that here to come. So in standard machine learning, we're trying to take a bunch of x's, and we want to find a formula based on those x's that predicts a response. And the way that this is done, or the way that it's introduced in most cases, is we learn to partition our data set into a training set. This is used for fitting models, and then a separate data set of other observations that we use to assess or to tune that model. Now, in the context of DOE modeling, we're trying to do basically the same thing. We've got x's and we got y's, and we're going to find the formula that predicts them. But we don't usually use holdout type techniques. There's a whole lot of like 80 years of history of different tools used for fitting and assessing models and designed experiments. F tests, half normal plots. More recently, there's been a lot of interest in using forward selection and model selection criteria to identify what the important factors are. But why don't we try this whole machine learning idea of having a training set and a holdout set to DOEs? And the reason is that the reason we don't do that is because designed experiments are very, very concentrated in information. And if we were to remove observations from these carefully structured data sets, then the models are no longer identifiable, effects become confounded with one another, and the meaning of the fit, software will give you a model and it'll give you some warnings like lost DFs over here to let you know that something strange has happened. But what is really going on is the meaning of the parameters in there has changed and it's confounding the effects of, in this case, some of these interactions with some main effects. So let's take another look at this and think about, what kinds of things can we do? We have this data set and we want to solve this problem of finding a model to fit to it using machine learning. Maybe we could just copy the data and have the same data as the training set and also as the validation set. Why don't we do something like that? And that's because that's a totally stupid idea, right? Totally dumb. No one should ever do that. It's ridiculous. And the reason is that anytime, if we look at a plot of, goodness of fit, here I'm using a log likelihood function along an index of model complexity. Every time we add some complexity to the model, we're going to improve the fit of the model to the training set, which in that case will, by definition, also improve the fit of the model in the validation set. And so we'll always choose the most complicated of all models, and the model that results will probably not generalize very well at all. So that's ridiculous. So let's kind of back up even further and let's look at holdback validation as a weighting scheme. So we'll take our data here and we'll think of it as having two sets of weights. We have a training weight that is equal to 1 whenever we're in the training set and equal to 0 when we're in the validation set, and vice versa with a validation weight. So we're going to fit models using the training weighted version of the data and assess them on the validation weighted version of the data. Now, if we plot those weights, we see that the training weights and the validation weights are heavily anti-correlated, because whenever the training weight is equal to 0, the validation weight has to be equal to 1, and vice versa. So what if, instead of using binary values like that, we found a way to put these onto a continuum where we have continuous training weights and validation weights, and we construct them in such a way that whenever the training weight is large, the validation weight is small, and vice versa. So this is a little bit of a trick here to see if we can get some way of having some kind of independent assessment of goodness of fit without throwing any observations out or fundamentally restructuring the design and the aliasing structure that it has. And so one way to achieve this is by using a variation of the fractionally weighted bootstrap, where we create a bunch of uniform random variables between 0 and 1. If you run them through the exponential quantile function, you'll get exponentially distributed weights. And this is from the probability integral transform does this. It's very, very simple to see that. Now, this all depends on the uniformity of that of our uniform random variables. Now, it turns out, obviously, 1 minus u is also uniformly distributed, and we can run that also through the exponential quantile function, and we can get another random weight that is exponentially distributed, and in a sense, it's kind of maximally anti-correlated with the training weight. So here's a sample of something like 250 of these that we created. So we've got our training weights and validation weights constructed using this rule. We see that they're both perfectly exponentially distributed. And if we do a scatter plot of them, we see that they're also very highly anti-correlated. So if we have a very large value of our training weight, that observation will be contributing very little to the validation in a weighting scheme. We set with the extreme points there on the upper left-hand corner and lower right-hand corner. So the idea here is we called this auto-validation, and so we reuse the data. On the one hand, we use the training weights for fitting the model using things like least squares or the lasso or whatnot, and then we use for our holdout set the validation weighted version of the same data. And because these weights are anti-correlated, the observations that contribute more to training will contribute less to validation and vice versa. And the hope here is that this gives us something like an independent assessment of goodness of fit that is, it's not going to be as good as a true holdout set, but it's the most we can do, the best we can do with the resources we have in terms of numbers of rows. We tried a whole lot of different ways, or tried this idea of auto-validation, combining models, and did all kinds of crazy stuff in the early days of this research. And what we found was that doing an auto-validation procedure, fitting models using this this holdout scheme with something like forward selection or the lasso, and then reinitializing weights and doing this over and over again, and using an average across, we found that 200 replicates of this did pretty well. That was the best performing of all the things we tried, and we called this Self-Validating Ensemble Models, or SVEM. And one of the things that's kind of cute about this is that while each of the individual models that you fit using something like forward selection or the lasso will have to have the number of parameters less than the number of runs, the total SVEM ensemble can have more parameters than the number of runs. And so this is pretty interesting in that we're able to fit models that are supersaturated, not just in the potential effects, but in the it's also can be supersaturated in the active effects. And this technique works the best of all the ones that we've looked at in that particular context. So I'm just going to go through a couple of different sort of little visualizations to explain this. So the overall SVEM procedure is to initialize our training and validation weights. We fit a series of models using the training weights and evaluate them using the validation weights. Whatever model pops up the best is our final model, and we store it. We store the coefficients, and then at the end, our overall SVEM model is the average across all the coefficients. This is just taking advantage of the linearity of least squares models. This trick works only for linear models. You have to think about this slightly more generally in the context of other base learners, but for linear models, this is it's still pretty simple like this. So you start off with your data. You initialize your weights, you fit one model, then you set up your weights, fit another model, same thing over and over again, do this 200 times or so. And the initial SVEM model that we considered was just the simple model or average across all those individual models. So I'll just go through this with an example. So we've got our predictors here, a response. This is the actual uniform random values, and the training and validation weights constructed using just the quantile function for the exponential distribution. So we fit a model to that. We save out its prediction formula. In this case, we did forward selection. Forward selection for that step happened to pick two main effects. Then we reinitialize our weights, try it again, get another prediction formula. This found another model with a different set of main effects, interactions, and I don't see any quadratic terms there. So it's a little bit more of a complicated model. And we just keep on doing this over and over again. In this case, it's just 5 times, but we would usually do this 200 times. And our final SVEM model is just the average across all of these individual predictions. And this was the model that resulted in this particular case. So I just want to stop real quick and see if there are any questions in the audience. Does everybody kind of understand the idea here? Is there anything that I could make more clear? So we're all good? All right. So early on, we tried a whole lot of different ways of applying this auto-validation idea. We used a lot of different base learners, such as the lasso and forward selection. We attempted to do the Danzig selector, which gets lots of had a lot of interest in the DOE research community, but for very technical reasons, we had a hard time figuring out how to actually do a weighted Danzig selector. So we were unable to work out a SVEM Danzig selector. That was actually the only one that we couldn't figure out how to do. We tried looking at single shot auto validation, so that would be just doing this once. If that would have worked, it would have been nice because it makes everything a lot faster. We also investigated calibrating our models using a null factor. So you add an extra factor to the inputs that's just randomly distributed and changes from bootstrap iteration to bootstrap iteration, and then use the frequency with which that term entered into the model to find any factor that occurred in the model as many times or less than an independent random variable shouldn't be that important. So we would prune afterwards, but that didn't really work out very well. It degraded prediction performance. And we also found that in very small sample sizes, your final SVEM model would have actual biopredicted plots where you want them to be along a 45-degree line, but they would be shifted away from that. And that was caused by having a large number of individual models that were just the intercept, where no terms had been added to the model using the lasso or forward selection procedures. So we, to sort of adjust for that, we regressed the SVEM model average onto the responses and then used the results of that linear regression to kind of rescale our predictions to get out of that situation. And we found that it improved performance in small samples, and in other situations it didn't hurt. So now it's part of the way that SVEM is implemented in JUMP Pro 17. So I'm going to go over a case study. So this is a designed experiment that was run at a biotech company up in New England. Phil Ramsey was working with them. They were trying to maximize yield of a plasmid DNA. I guess that was the component of a drug or a product that they had. And so they did a 5-factor designed experiment in pH, dissolved oxygen. There was an induction temperature, and there was some kind of an optimal density parameter that I don't understand. And there was a feed rate into the fermenter. And the result was this pDNA titer. And this study was done a while ago, back when my colleague Bradley Jones introduced definitive screening designs, which were kind of a radical breakthrough at the time. And so Phil did this study with this biotech in 2 stages. He did it once as a definitive screening design in 15 runs, and then also did a central composite design in 31 runs. And he wanted to, sort of verify that the 2 designs led to similar results. So you could actually get away with the 15 observations in the DSD. We had this data sitting there, and we used this as a tool for assessing SVEM on real data. So we applied the SVEM technique to the DSD runs, which were supersaturated in the effects, and we used the central composite design runs as a true test set that was independent of the data that was used to fit the model. So there's the complete data. And so we initially looked at fit DSD, which is a technique in JUMP that takes advantage of the special structure of definitive screening designs. We also looked at forward selection using the AICC model selection criteria, and also SVEM using forward selection built around this whole ensembling of auto-validation concept. And when we looked at the R squareds on the test set for this, on the CCD runs, we see that fit DSD and the forward selection with AICC both got R squareds on the test set of 22 and 0.22 and 0.24, and SVEM got more than double that. So this was anecdotal evidence that our technique was doing well in these supersaturated situations. We were explaining twice as much variation as the existing techniques. And so then we did a whole lot of simulations, and that was Trent Lemkis's the bulk of his dissertation. I'm only going to give you some of the a very small subset of the situations that we looked at. I tried to choose ones that were kind of representative of the overall patterns that we saw. So the first set of simulations that we did was using BEHNKEN designs in 3 and 5 factors. So these are designs where the number of runs exceeds the number of factors. So it's kind of a relatively standard, it's a classic design. We looked at a bunch of different fitting techniques. So we looked at straight forward selection with the AICC, something called pruned forward selection. This is a mixed mode where where JUMP is able to, it'll add terms like forward selection, and then it'll also, if it thinks it's optimal to remove a term, it'll take one out. We looked at the lasso with AICC, the Danzig selector with AICC, and then 3 versions of SVEM based around forward selection, pruned forward selection, and lasso. We looked at various values of our residual variance. So we let sigma equal to 1, and also in this case we looked at sigma equals 0.3, so that was a low signal to noise ratio. And for each of these simulation runs, of which we did 1,000, we would randomly generate a set of betas with a mean, regression coefficients with a mean of 0 and a variance of the square root of 2. And we looked at 3 different amounts of effect sparsity. So A equals 25% there. Those are results for when only 25% of the betas were allowed to be non-zero. 50% for A equals 50% was half of them, and then we would allow all the coefficients to be non-zero in the A equals 100% case there. And so we looked at all these combinations, and we used a test set log root mean squared error. So we generated a space filling design with 10,000 points and over the factor region, and we used the the true model to assess how close each of these different fitting techniques was to that truth. And overall here, the results were sort of not super exciting. So this was an unsupersaturated situation. Smaller is better in root mean squared predictive error. And we saw that the lasso, Danzig selector, and SVEM techniques performed similarly in the only 25% active case. There was very little difference in the 50% active case. But then once we had all the effects active, it looked like, the evidence was that there was a slight difference where SVEM was more accurate than the lasso and Danzig selector when all of the factors were active. So this is a common situation. So this kind of common classic situation served as a evidence that like we weren't like doing anything really ridiculous. It's hard to beat least squares because it's the uniform minimum variance unbiased estimator. So that's available. We're probably just never going to be able to beat it. And so the stability here was, in this context, was kind of satisfying. So then we moved over to definitive screening designs, and we looked at the number of factors equals 4 and 8 situations. Now these designs have more parameters than we have unknowns, and so there is no least squares estimator. We compared the RMSPE again for those, and we found that as the amount of active factors increased, the SVEM methods pulled ahead of the rest of the pack. So if you had more parameters that were active than there were observations in the data set, the most accurate of the techniques were the SVEM-based ones, and there wasn't a whole lot of differentiation between the different base learners combined with SVEM. 4 minutes, okay. We also did a sample size study. So here we looked at a series of designs of different sample sizes and different different designs, okay, central composite designs, d-optimal designs, I-optimal designs, and Latin hypercube designs. In general, so this is log RMSPE again. The green and the purple are the SVEM methods. So they're generally the lowest when we're looking at the n equals 13 and n equals 20 supersaturated situations. When we get to n equals 28, we now have 7 more runs than we have parameters. And so the best model overall happened to have been the forward selection with the AICC, which is kind of not so surprising because we're in a situation where we have enough information to fit the full model. D-optimal designs did poorly in supersaturated situations for prediction, and but I-optimal designs and Latin hypercube designs both did well in the supersaturated case. Once we got to n equals 28, the central composite design kind of pulled ahead of everything else by a little bit. These plots are, it's a little bit anecdotal here in this sense, but we do in the dissertation, which I'm happy to share with you, have like statistical tests confirming all of the results that I'm describing here. And I'll conclude. So overall, what we felt was the overall winner was SVEM and forward selection. So it did generally about as well or better than any of the other techniques in these supersaturated situations. Other people have been looking at this. They have found that like when you're looking at 2-level screening designs or any kind of screening situation, this doesn't really offer much help. So it's in those cases, the classic techniques work. So this is more of a response surface methodology. There's been lots of interest in applying other base learners, such as neural networks, which my friend Jim Wisnowski will be talking about here in a minute. And overall, we see this as a very promising technique that needs a lot more work because we need to develop model diagnostics to assess when the fit is not adequate, and we have a need of things like uncertainty quantification, like probability intervals on our predictions, and we don't even really have a reasonable estimate of the error variance yet. So there's still foundational things that we need to do, but we have seen that via simulation that this has a lot of promise, and our friends in the field have also had results showing its promise, such as Jim Wisnowski will be showing here in a minute, and we've had lots of interest in the biotech industry where they've been using this successfully there as well. Thank you very much.
Okay, I think we have time for one question. There's none in the chat. Does anybody have a question for Chris? And I'm sure he will hang around after Jim's talk so you can catch him then, but we have a question right here.
So I know it uses some bootstrapping methods, and I was wondering in all the comparisons you did, if you compared it to doing bootstrapping on the data set and then making modeling and how that looked with everything. And maybe the answer is no, but
Well,
I
so
figured.
there are obvious problems with resampling based bootstrapping in the context of design experiments that we didn't look at that because we felt that the aliasing that would be induced is was kind of obvious to us that that wouldn't work. That is still a rock we haven't looked under. I invite you to take a look at it. I'd love to know the answer. We simulated ourselves to death, and so we can only look at so many things. But that's one of the obvious questions that someone should probably look at.
All right, let's thank Chris, and if you have questions, catch him
Yep, I'll be around.
after Jim.
Yep, thank you.